Good morning, everybody. Today I'm going to spend a little bit of time. Yesterday, GOG announced, maybe it was the day before, that they were releasing The Summoning. Now, The Summoning is a game, I want to say 92, 93, maybe 91 even. Let's see, 92. It's a game for DOS that is really long. It's an isometric RPG. And includes a whole bunch of really cool file formats. I love file formats. I love to explore them. They're like a puzzle that we can dig into. Usually I don't play games on the stream. Usually I just code. So I'm going to start, though, just by showing what this game looks like. Let's take a look. So this is DOSBox. I actually use a slightly patched version of DOSBox where I've stuck in a whole bunch of, or I turned on debug mode, and so you can see here's the data overview and so on. So if I run it inside debug mode, it'll do that. But I also include a whole bunch of logging stuff that I added in to trap the interrupts. So if we run, I'm going to cd into my directory for the summoning. And I'm going to run it. You can see here I've got a whole bunch of interrupt traps. I'm not going to go through those right now, but I will talk about them a little bit later because they do factor into this. This is the startup screen for the summoning. You see it's got some pretty cool animations, very much of the time. The summoning was created by a company called Event Horizon, which later became Dreamforge. David L. Craddock's book Game Dev Stories Volume 5 includes a little bit of information about this. One of the neat things about Event Horizon and then Dreamforge is that nowadays Dreamforge has been brought back by Scott Knoll and I think Jane Knoll as a magazine of sort of hope punk modern science fiction. So this is what the game looks like. I'm just going to start up just very briefly because the point of this isn't really the game. The point of this is going to be looking at the file formats. I remember when I was a kid playing this, it was we'd have to stop and whatnot, and it was always kind of a pain in the butt to wait for all of the stuff to happen. You have to wait for all the different interactions to go through and whatnot. Let's see, page 38. That is going to be, let's see, this guy, two of that guy, that one, and then our old friend Will Riker once more. And I'm just going to select a pre-generated character, and you'll see why in just a minute. There are three of them, Johansson, Darchase, and Larimore. Let's go with Darchase. Just going to go ahead and start the game, skip the opening. So all of these different things that we're seeing are assets. And actually down here you can see one of the things the summoning does is it reads the files just as it needs to. So it's reading all of these different icons and assets as it goes. It keeps very little resident in memory, if I'm remembering correctly. And I'm just going to walk around for a moment to show you what the level looks like. It's isometric. You can see there are a number of different tiles. And then as I walk, we've got, I want to say like 7 or 8 frames of motion. Okay, now here's an item. I'm not going to do much more than that just now, but that's the basic gist of it. Let me go ahead, and there's one more thing that I'll show before I quit out, and we will probably not play any more of the game, which is important for... So I hit C, and I chatted. Now I want to point out a couple things. See, there's a little bit of a headshot there. Hello, Darchase. I am Malachi, secret messenger, blah, blah, blah. See, we get text in these chunks. And then you'll note that when we get to this part, one of these is underlined. The first magical seal. Okay, so then we get here, and we can type something in, or we can type first. See first, and it gives me a couple other things. There's a plot here, and the game is like 40 levels long, and they're all pretty long levels. Well, this level's not, but you can also type here something like coins. And so you'll see that you can ask for things, and then if we chat once more, it gives me the same thing again. We can actually type, yeah, can't do all of it, but I can type buy, and then we'll be done. Okay. Let's see, I can never forget how to get my, let's quit out. What's the, no, that's not it, but we'll come back to that. Oh. Let's go to the game menu, and we'll quit. All right, so that's the extent of what we're going to look at here. Let's take a look at now where we can go from this. I've got my chat window back up, so I realize I didn't for a little bit. So let's take a look at what we have inside our game directory. If we look at this, you see there's a whole bunch of leftover junk from where I've been working on things before. There's summon.com. If we look at file summon.com, you see it identifies it as data. If we look at file code.1, you'll see it's an MS-DOS executable. And really, if we look at that a little more in depth, you can see it knows that because it starts with MZ. So what is it we want to do when we want to explore this and try to reverse engineer it? Well, we're going to use a tool called Kaitai. And we're going to start with the assumption that we're able to figure out what is in which file. So if we just look at one of these things, so let's say we'll take a look at text, see that it looks like a whole bunch of files. Now if we want, or it looks like a whole bunch of data. If we want to read this a little bit more clearly over here, this is a, let's see, it looks like it's 8 digits long, and this is the location of the start of this line. And then we've got our hex codes, and then if they're able to be transformed into printable ASCII, it puts them over here. I don't think it does any of the code page 437 stuff in this. And if we look at the text file, you'll see there's, well, a lot of stuff that we can't really interpret. So how exactly are files written when we want to be able to do them? And you'll note, or when we want to be able to query them and access them and look at them. Now, my day job is in the field of information science, where I work on data analysis, particularly for large-scale simulations of the physical environment and so on. But today, we're going to look at how that is relevant here. So let's take a look at this inside IPython. Now, I'm going to use IPython just because it's a little bit easier to quit in and out, and I don't have to get my window up. But we're going to look at these things as streams of bytes. So if you recall, when I looked at this inside XXD, it wasn't able to parse all of these things. So let's take a look at this. Now, these are in hex. If I were to grab the entire contents of this file, I will grab it as bytes. So we'll call this text equals open text RB, and then we'll read it. Oops, sorry, I got ahead of myself. If we look at the length of it, it's that many bytes long. And if we wanted to look at this as a set of unsigned integers, we could do from buffer on text dtype equals U1. We'll call this BT for binary text. And if we look at the first 10 digits of it, we see that they can be interpreted as 16, 17, or 16, 7, 0, 0, 6, 8, 2, 8, blah, blah, blah. So this isn't necessarily what we actually want to figure out, right? This isn't a readable set of text yet. And what we need to do is we need to figure out how this information gets translated into text that we can view. So if I were to view this as a different set of data, let's take a look at it if we were to view it as a set of 2-byte integers, unsigned. See, now it's starting to come a little bit more into focus. Okay, so the first one is 1808, then 7236. You know what? Let's take a look at the next couple bytes a little bit more. Well, that's interesting. And if we look at this as U4, see here, looks similar. I'll talk about the difference between U2 and U4 and why we might use them in different cases in just a moment. But here you'll note that this number in unsigned integer 4 is 1808. And then all of a sudden, we've got this string of values that look like they are monotonically increasing. And in fact, as we start looking further and further out, that is borne out. So let's see, what happens if we do starting with 1, and we look at, here, let's take a look at this, BT, and let's start with 4, because this first one, that doesn't really seem to fit. The rest of them start around the same area. Let's do 4 out to 256. Let's do 1024. Oh. So let's try this. We'll call this table 1. So let's see. Does this monotonically increase? Yeah, it does. All right, so let's go back to what we're seeing here. And I will tell you that I knew the answer to this question. I did my homework on this one. Let's take a look at table 1, 0, 7236. All right, let's try this. So let's say that we assume every single one of these is that the table is in fact 7,236 entries long. Oh, I'm sorry. No, hold on. Let's say that the table is 1,808 entries long. So if we wanted to explore that concept, let's take a look at starting at byte 4, going out to 4 plus 1808 times 4. Okay, so let's call this table 2. So this is if we take our binary text file and we look at it stripping off the very first 4 bytes out to that first 4 bytes in entries. Let's do the same thing we tried before to see if they monotonically increase. And they do. Now let's see what happens if we look just beyond the end of that table. 4 plus 1808 times 4. Oh, all of a sudden things start getting a little bit weird. Okay, well, that looks like it's the end of our table. So if we return to what we see here, the very first set, 1007, which remember we're dealing with little endian, so it's hex of 0710. This is the number of entries in a lookup table. That lookup table requires that we have extra long, so 4-byte integers because it's a big file, and it has that many entries, and each entry points to a position in the file. Because the very first entry starts right where the table ends. So we want to figure out what can we do with this information. We're going to use a tool called Kaitai Struct. Kaitai Struct is a mechanism of describing binary file formats with a variety of different logic controls as well as type variables and things like that. And the concept behind it is that you start with a KSY file, which is a YAML file. It gets run through a compiler, and then that compiler can generate Python, JavaScript, C++, and a bunch of other types of code as well. So we're going to take a look at this using what's called the Kaitai Struct visualizer. I'm a little bit torn here as to whether or not I want to actually show the file or if I want to talk about developing it. I'm going to start with developing a new file, and then we will take it from there. I will show you the results in just a moment. We're going to call this text.ksy. Kaitai structs have a variety of metadata that they can accept, but we're going to start out just with the very basics. You can define things in terms of either instances or sequences in Kaitai struct. We're going to start with a sequence. The very first item that we have is the count. And recall that we said that was an unsigned integer 4. And then we have what are called, what we're going to call offsets. Each one of these offsets, which as we determined is of type U4, is going to point to a given location in the file. We know how many there are going to be, and so we utilize what's called a repeat expression. And we're going to say repeat up until you hit count. Now, let's take a look at what this looks like. We're going to use KSV, and we're going to supply the KSY file. And this is a little Ruby-based visualizer. You'll see it's got the hex, it highlights where I'm at, and then if I look here, each one of these offsets is loaded. Now, if you put yourself in the shoes of a game developer that can't store very much information in memory at once, and you want to be as conservative as possible in terms of that memory, this is useful because it tells you exactly where to read in the file. If you know that you need text ID 19, you can read, you can open, seek, read, and then you've got your data. So now let's take a look at what we can do once we have that information. We're going to start with a hypothesis. I hypothesize that we are going to then have text available to us. We know exactly how much information we need to read, but there's a little bit of a trick here. If all of these files with all the different text were available, then we could just run then anyone playing the game can figure out what they say. But that's not really how they want it to work. A very common system that they used for obfuscating this information was XORing something. So if I had a simple text string and I XOR that with 10, see it doesn't work there, we'll call this S equals a simple text string. We can turn each one of these values into an integer. And that's how it's represented. And we can go backwards with something like this. So if we were to do ord see, this gives us our ordinal, our integer representation of each one of these in ASCII for the time being, for each one of these items. Now, if we wanted to obfuscate that somehow, we could add it, or we could XOR it with something like 89, and then that gives us our output value. We can see what that looks like. See, it looks like a bunch of garbage. So, why don't we read a string from our file? Oops. So we've got bt is np.fromBuffer. So let's see. Let's take a look at, we know this is where we want to start. So this is our text. So let's take a look at table, let me go back to our visualizer. We're going to take a look at a reasonably small set of values. We'll take a look at, well, we want it to be long enough that we have something to look at. So let's take a look at one of these. 58 through 93. Let's do 10446 through 10474. Text entry equals BT 10446 through 10474. Did I get that right? Yeah. Okay. So now this is a text entry, and if we look at this, it looks like, well, like garbage. So we suspect, and I actually happen to know, because I've done this before, that this is XORed with something. So let's figure out what it's XORed with. For I in range 256, print text entry XORed with I 2 bytes. And let's also do I so that we know what it looks like. Not looking good. Wait. That looks good. So, 218. All right. I mentioned that XORing something is a very common thing to do. It's so common, in fact, that Kaitai Struct has a set of values for it, or has a built-in constructor, or built-in XOR operation that you can apply. So we're going to call this ID text. We'll call it type XOR string. That is not a type that Kaitai recognizes. We're going to create it in just a second. We're going to do repeat expression up to count. So now Kaitai can also accept special types. We're going to call XOR strz. XOR str. This is going to be a sequence. It's going to have an ID. The first item in it is going to be ID. We're going to have it process with an XOR, and you remember we saw it looked like it was 218. And it's terminated with a null string. We're going to have instances inside there with a value of a new type that I'm going to define. It's encoded in ASCII. And the terminator is 0xDA. So now, when I look at this inside that, I've got what's called an instance, which is declared on demand. The value of that instance, here you'll see, is beginner. And what it's doing is it's XORing my initial set of values with this in order for me to be able to see it. Where do you want to save this game? So it's translating this 8D, B2, BF, A8 into 57, 68, 65, 72, on and on and on. Now, let's take a look, see if we can find our first dialogue. Which we looked at when we were in there. These are all various different things. Ooh, what's that? Your %s vanishes. Okay, so looks like it has some element of string formatting. We're going to come back to that in a minute. Your spell points require no rest. Create new directory. So far, this is all stuff that is probably related to built-in things or not necessarily dialogue trees. But let's see if we can find our dialogue tree, the very first one. So keep skipping down. Every element of text in the game has to be represented here somewhere. And that's actually not true. There are some elements of text that are represented inside the executable. So let's take a quick look here. This is starting to look like we're into the level names. This is going to become important in just a minute. Yeah. Hey, Bogus. So when we do this, we want to make sure that, let's see. Oh, you know what? I made another diagram that I forgot to show. How do I pop this out? Basically, there are two different ways that we typically find records stored, either through length embedded records, where you can read the entire set of records at once, and then you construct an index as you go. This is what the summoning does in some cases, but not most. Random access is really just not feasible in this particular instance because you have to accumulate as you go through the file. Indexed records, though, where you start with a record table, which has a count and then a set of positions, or which is basically a file allocation table, allows you to do a much shorter process of reading and indexing. So you get the record number, then you read, and it consists of 2 seeks and 2 reads, I believe, in order to get to the exact number of the exact item that you're looking for, which is a pretty useful way of reducing the number of file reads. So, the next thing we're going to take a look at, now that we've figured out where all this text is coming from, is we're going to see if we can figure out, oh, there's the copyright. There's some credits. Let's keep going on down. There we go. Now we're getting to some dialogue. Looks like somebody's talking to him about magic spells. And I want to point something out here. You'll note, it is you again. I see that you are still alive. Have you taken my word and avoided the many dangers? And you'll see there's an asterisk there. That asterisk is going to be important because if you remember when we looked at this inside the game, let's get back to see if we can find Malachi here. He should be one of the very first ones because he's the first character you interact with. Here we go. So you see here's Malachi's first entry. Hail, and then there's an at. You recall when we played the game, we actually saw Malachi called you by name at that point. I'm Malachi. So at is the symbol that they replace with the character's name. And if we look over here, here we go. You recall that when we got to this screen of dialogue with Malachi, first was underlined. So we've already started figuring out that it does percent-based string formatting. Asterisks indicates that there's a keyword that needs to be underlined and that's potentially selectable. And the at symbol gets replaced with the character's name. So we've started getting an idea of what the text might look like. So now we would expect that at various different points, we will be identifying that, say, during character interaction and so on, there will be some type of a dialogue tree that indicates when different items are called up, telling the game to load particular record numbers. So let's take a look now at the levels file. I will say that I've made a fair bit of progress on decoding a number of the different resources, and so I'm not going to get to it today, but I do have a full dialogue tree constructor for the data in this file, and it comes from a file called interact. Interact is essentially a set of bytecodes that describe when and how different messages get sent out. And one of the neat things about this is that sometimes they wrote out to disk they would occasionally write out to disk uninitialized items, and so you get little bits of RAM, leftover allocations and so on mixed in. All right, I'm going to take a quick look now at one of the more fun items that we can look at, and that's the levels file. So let me go ahead and show you. This is the clue book for the summoning, and it's like 200 pages. But this is the antechamber where we started. So this 1 is where you begin the game. 2 is Malachi, and then you'll see there are these 2 different passages. There are things related to X and Y dimensions. There are movable items placed in the room. There are doors. There are tiles on the floor, tiles on the wall. And so let's see if we can make some sense of this levels file. I'm going to go back into IPython. We're going to load NP. We're going to say level text is equal to open levels, read binary, read the whole thing. Let's get the len of that. Okay, 269,726. So let's see what we can do with that. Let's do np from buffer. Oh yeah, Focus, I would love to do that. I am absolutely excited about that prospect. So let's take a look. We're going to take from buffer here. We're going to say dtype equals u2 because I think that's what it is. Nope, looks like it's u4. And actually, let's take a look just at the first 4 bytes. Looks like 41. So if we go back to our notion of the, let's see, it's this one. The indexed records with the record table, record count, and then all the different records. Let's take a look at that. So let's do all the way up through 42 times 4. This looks suspicious. 41, 168, 1028. It's monotonically increasing. We have 41 entries, and the last one starts right before the end of the file. All right, so let's start writing that out. Let's take a look at the distance between ones. Let's take a look at our first record, which we assert is going to be level 1. All right, sure looks like something. Let's go back to level 1 equals level 1 as type u1, because it's always easier to start with this stuff in binary, or in unsigned integers. Now I'm going to cheat. I've got in another window some of the results of when I reverse engineered this. I guess it's been years now. But the very first thing that we have when we see this is we have what's called a header inside our given level. And that level, let me see, that level header consists of a couple particular sets of items. The first one is a height and a width. Now I know this because I did a whole bunch of experimentation, but we can also figure it out just from looking at our map. This is kind of a neat thing here. We can, in principle, the clue book I figured out was actually automatically generated from these level files. There may have been some modifications done to it, but it was automatically generated, and we can actually, if we draw a line here, and then we duplicate that line, and we rotate it. Oops. Actually, you know what? Looks like I can't rotate it very easily. We rotate it, we can see that, yeah, it is actually 18 by 24. Each one of these here, it's in integer values, so this is 1. It's the smallest increment that we can do. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 16, 17, 18, 19, 20, 21, 22, 23, 24. I guess I counted wrong. So it is 18 by 24. And then we've got a whole bunch of data here. And that data I was able to determine are actually what's called level props, or what I call level props. And they basically say, for this level, what are the individual sets of tiles that are used on the ground? What are the tiles that are used on the walls? What are the tiles that are, or what is the big wooden floating thing? What is the big boulder? How do you define the switches, and so on and so forth? And then there's a whole bunch of blank data. The next thing that happens is that there's a set of, well, you know what? It's probably easier if I just show the results of this. So we've got our levels. There's a file header, just like we talked about. And then for level 0, we've got, oh, it's width of 26. I misread. Did I? $24. Huh. I'm going to have to figure that out. Did I accidentally grab level 2? No. All right, well, I'm going to have to dig into that because that's confusing. But we've got properties. This tells us the internal wall edges, and so these are all offsets into various different sprite categories. And then there's a map, and this map is exactly 18 by 24. So you see it's highlighting 234 through 702. So let's quick run that up, 234 by 702. I'm sorry, 702 minus 234, and then 18 by 26 gives us 468. So this map tells us which tile is where, and it's actually a pretty straightforward mapping. These tiles are double size because it's isometric, so when we look at our pixels, we actually stack 2 sprites on top of each other. If we translate this map directly into a set of data, we can reshape it and we can see it in our given values. And so I'm actually going to do that here. So 234 through 702. Let's go back here. LT is equal to levels RB, 234 through 702. np.from buffer, LT 234 through 702. dtype is equal to U1. And so this gives us our array. So this is our level map. Now there's more to a level than just this. But here, if we reshape this 18 by 26, and if I make it, let's transpose it. You can kind of see it here, but the 255s really do get in the way. Actually, I wonder if view as I1. That doesn't really help. The minuses really do just as bad. So let's do for row in level map.reshape 1826 print. Let's see. We'll join this with there we go. Oh, space 4D. There we go. So now you can actually see this is the map. I was able to figure out at some point that that there are different categories of these, because typically you would pack multiple pieces of information into a single 8-bit value, for instance. So 27 is a type of floor tile. It's 28, 27, 36. 36 is actually a special one. There's other metadata that's associated with this later on in the file. 255 means empty. And one thing I want to point out is that there's a secret room here. If you say Zebu to the very first character, it shows up. So each one of these values can be mapped into a particular set of values, and now I wrote up a little script to do that. I actually really like the code page 437. Let's see, does this do it? Yeah. You know what? I'm gonna do just very first level here. So I've mapped this to code page 437. You see, this is, I want to say it's like I think it's one of the like talking skulls or something like that. And these are the walls here, and each one corresponds to whether it's a corner, which particular type of corner it is. And then you've got multiple different types of flooring in there as well. I made a slightly nicer one. Let's see, level viewer, yeah. Here. Now I haven't fully fleshed out the values, but you can see that as we scroll through this, each one of these is a given level for the game itself, and there are a ridiculous number of levels in this game. In fact, there are 41 of them. So you might be wondering, how do we translate this into images and so on? Let me quick go back here. Inside the directory, there are a bunch of different items here. There's things like jazz, which, if I remember correctly, is the music. There's NPA. The goal of this project for me, Bogus is asking in the chat, it started out just as a puzzle. I wanted to solve the puzzle of how they stored things. One of the things that, as I was reading about, how they would store files, how, in the earlier days, and learning about compression algorithms and so on, which take up a lot of my mental space at work, I spent some time learning about how people used to do this, and it was just such an amazing craft that they would have. They would optimize for a particular thing, and then they would need to map that particular thing. And so I really wanted to know how this game was constructed. I do eventually kind of want to create. I don't actually think I could create a lot of content, but I have spent a little bit of time exploring the notion of exporting from this to like the NPC interactions into something called Twee, which is the Twine markups. It's something that compiles into Twine and so on. But you can do a fair bit with it. And you know what? Let me show, because I actually have a good amount of progress on this. It's not complete, but I've done a fair bit. And one of the things that I really like is that it's pretty straightforward to construct widgets with this. So I've got a database system called dispersing, because like the summoning, dispersing, they're sort of opposites. And what it does is it pulls up sprite information based on different NPCs and so on. So here, let's do this. I spent a bunch of time figuring out how you get the names out and things like that. So let's take a look at Malachi. Here's Malachi, the head, and here are the different frames for his NPC animation. Let's see. Here are the different tiles. So here, these are the tiles. Info is a given tile. Some of these have different different items on them. So you see there's a falchion. We saw this earlier on when we were exploring. You've got different items that are on there. And then this is actually the secret room up here. You can get all these different skulls to skip all the way to the very end of the game if you say a particular thing to Malachi. And then there's stuff like, all these different NPCs, and they've all got headshots. Let's say we wanted to, is it sprites? Yeah. So this looks like a set of sprites for a particular healing potion. This is that. And then we've also got stuff like, let's see, objects. let's do, let's take a look at the chest. There are its items. But I've also been able to debug a couple of the records and so on. So let's do ts.objects chest record. And so this record has stuff like the AC bonus, the damage that you get with the action 1, the number of charges, some things I haven't figured out like the column, the number of items that it has. One of the neat things that I really like about this game, which was very frustrating to me when I had a very small hard drive 30 some years ago, I guess at most 31 years ago, was that because each one of these objects is manipulable and changeable, like the number of charges goes down, it can get damaged and get broken and things like that. It has weight and so on. Is that whenever you saved a game, it actually stored the entire state of the level for every level that you visited up to that point, because in principle you could backtrack all the way from the very end to the beginning. I think there might be some firewall at some point, but I can't quite remember where it was. Let's see. No, this is some debugging stuff. Yeah, here we go. And so we can also look at, there we go. This is what we want to do. We can also look at things like the levels and take a look at the terrain sprites for them. So this is level 0, and you recall this was the one that we started out in. And then you'll see that here are internal wall edges. Now each one of these has a top and a bottom offset by 15 from each other. So this is the bottom for this. So if we look at 1 and we look at 16, see that they're offset exactly. Each one of these is drawn in the isometric view. And I'm working on getting a full rendering of it, but I keep running into issues with it. There are different floors, and I haven't quite gotten the, you'll note that these colors look a little bit off. The way that they store colors in this is a little bit different than what I would have expected. Let's see, assets, colors. They store palettes. So you've got palettes here. And each one of these is, oh, I guess this is a list. You see each one is an RGB color. And I haven't quite gotten the palettes right for some of the active things. They often do multiple palettes for these so that you can do animations. And these are the special tiles, and each one of these is tied to a particular item inside the level values themselves. And you can get big wooden things that follow you, boulders that roll along and damage the character and so on. And you can also get little decorations on the walls. Okay, so I'm gonna stop there just because I realize that I am feeling myself. There's a line in the book Good Omens where he describes skidding around the edge of a deep pit, and I can feel myself doing that just now. I really want to fall right on into this and do a whole bunch of work on it, but I've got to, unfortunately, do some other stuff today. I'm going to come back to this because it's super fun, and I'm going to tie it to how we might use Kaitai Struct for some other cool things. I really appreciate you coming, Bogus, and hope to talk to you all soon. Thanks, everyone.